Okay, so scientist by the name of Gibbs, an American scientist, this is in the early 1900s, realizes that if we put together these two concepts of delta H and delta S, it can be mathematically used to determine whether a reaction is spontaneous or not. Now, not only is it used to determine whether a reaction is spontaneous or not, but the combined effects of the delta H, which is the thermal energy, and the delta S, which historically was that energy came from the piston moving, if you combine those two effects, then you end up getting a total amount of useful possible energy that can come from that chemical reaction. The thermal effects, plus the work that can be done if that heated gas is driving a piston up and running an engine. So the Gibbs free energy, not only does it determine spontaneity when we put them together, but it also gives a chemical engineer, say, a useful calculation to determine how much energy can be derived from that particular chemical reaction. Does that chemical reaction have a lot of energy in it that can be useful, maybe in running a car or running some kind of an engine, or is it not useful? All right? Now, change in Gibbs free energy. How do we calculate this? Because again, it's the change that's really important. Here's the mathematical combination of those two factors. There's our delta H, and then minus T delta S. The temperature must be in Kelvin, okay? If you recall, right, the delta H, oops, oh, don't tell me that's not functioning. It isn't. That's absolutely terrible, and I've got to write on this. I'm going to back up here for a minute. Okay. Okay. So how does what we just learned in the video from the other day, how does that version of being a spontaneous reaction kind of work together with delta G? Well, again, it has everything to do with the signs. Notice in our equation here, the delta H has the same sign as the delta G, but the sign in front of the term that contains the entropy has a negative sign. What that means is the sign of the delta H is sometimes the same as that sign of the delta G because they both are the same sign. If the delta H is negative, it's spontaneous. Right? We learned that just the other day. And therefore, because these have the same sign, when the delta G is negative, that also corresponds to spontaneous. Because the delta H and the delta G have the same sign in that equation. We know that for entropy, when the entropy is positive, it's spontaneous. In order to make it work in this equation, because I can only have one sign for delta G, scientists, Mr. Gibbs, put a negative to change the sign of that positive delta S and make this mathematical term become negative, which means a positive delta S will become negative. That, along with a negative delta H, makes a negative delta G, and it's spontaneous. So the negative sign in that equation changes the sign of the delta S. Okay? If the delta H was positive, then the delta G is positive, non-spontaneous. If it's non-spontaneous in terms of entropy, then that has to be a negative number, but notice the negative turns it positive again. And therefore, a positive and a positive is positive. So a delta G that is positive is non-spontaneous. Okay? Now, if we have that situation where the signs are the same, let's say I have a negative delta H, spontaneous, and I have a negative delta S, non-spontaneous, and that turns it into a positive, then I have a positive fighting a negative. In other words, I've got that scenario where they could cancel each other out. The spontaneity of the one might cancel out the non-spontaneity of the other. And that's going to be true if the signs are the same. If the signs are the same, you could have a situation where this negative cancels both terms and I get an answer of 0 for delta G. And if that's the case, then the entropy effect has canceled out the enthalpy effect, and we have what we call an equilibrium reaction that's pushing in opposite directions at exactly the same speed. No one wins. The reaction is going in both directions at the same speed, and it just kind of sits there because reactants are becoming products and products are becoming reactants. And that happens when we have the same sign. All right? So that's how the delta G can work. If I get a negative delta G, spontaneous, and I can get some useful energy out of it. If I have a positive delta G, non-spontaneous, and I have to actually put energy in to make it happen. I have to put that value of energy in to push the reaction to go. If I have a delta G equals to 0, then they're running in both directions simultaneously, and we've got this equilibrium situation where they're heading in both directions. Energetically, one is feeding the other. Let's take a look at the temperature effect on this equation. Again, you don't necessarily need to rewrite it, but you can if you'd like. Due to the fact that there's a T in the equation, the temperature is going to change the value of the delta G. So as we change the temperature of a chemical reaction, whether we change the, we put it in some kind of a vessel that we can heat, say with a hot plate or a Bunsen burner, or we could cool maybe with an ice bath or in a refrigerator, or even colder still, maybe using some dry ice or some liquid nitrogen or something like that. Because there is a T in that equation, changing the temperature changes the delta G. Which means you can actually change whether a reaction happens spontaneously or not. Again, if the signs are the same and they're trying to cancel each other's effect out, by changing the temperature changes the numerical size of this back-end term. Notice the delta H does not have a T associated with it. It means that the delta H for a reaction is set by the reactants and products. You cannot affect a delta H by changing a temperature. The amount of energy available from a chemical reaction is locked in by the identity of the reactants and products. But entropy is a temperature effect. The hotter you get, the more entropy something has. It's more chaotic. So let's say that we're cooling our experiment and we're making this T a tiny number. If this number is small, then a small number times another number is going to be a small number. And when this number is small, in order to figure out what the G is going to do, all we have to do is look at the H. Because when this number gets small compared to this one, it's going to be a little tiny effect. I'm going to subtract a little tiny number away. Look at the delta H. Because at low temperatures, T times delta S becomes a tiny number. It doesn't affect the calculation. So at low temperatures, negative T delta S is small. Look at the sign of the delta H to determine if it's spontaneous. So then we'll ignore the entropy and we'll look at the enthalpy to determine whether it's spontaneous. If T is a big number, we go to high temperatures, then a big number times whatever number that is, will make it a big number. It will dominate over the delta H. It'll become so big, the delta H effect will be minute. We don't have to worry about it. So if I'm at high temperatures, the T delta S term is large. Look at the sign of the delta S to determine if it's going to be spontaneous. So delta G changes with temperature because it's linked into that entropy effect. Let's do some examples. You are going to need your thermodynamics tables. And here I've got a very simple reaction. This is H2O gas, vapor, becoming H2O liquid. It's condensing. And we're going to use the heats of formation and the entropy tables to calculate the delta H and the delta S. And this is something I'm hoping you're becoming good at. I'll write the equation down just for the delta H just to remind us. But delta H is equal to the sum times the coefficient of the heats of formation of the products minus the sum times the N and the heats of formation of the reactants. You know what I'm talking about? That's that equation that's using the tables. This one's nice and easy. You're looking for H2O liquid versus H2O gas. It's a small one, but it's still a chemical reaction. It's a physical change, but again, the product, 1, probably no need really to write that. And now I need that heat of formation of H2O liquid. What do you got? 0.8? Negative 285.8. We've got to keep in mind what the units are, but we'll put them down at the end. Minus 1. And now I need H2O gas. Yep. Negative 241.8. And you know what? If you've calculated, it's great. But when we do a question like this, it's not a bad idea to do them both at the same time, because now I'm just looking over at the S column right beside it. Right? So I'm looking at the S column now, because I want to know the delta H and I want to know the delta S. So now I'm looking just at the S column. And I'll take those numbers when you get them, or when you look at them, or you write them down, or whatever you're doing. Yeah, what do you got? 69.9, and sorry, the last one? 118.9? 118.9. So now I will take some calculated values. You did the calculation already. 188.8. And you were getting your answers from the video, right? That's fine. It's good. And the answer is 118.9. 118.9. And be very careful. Delta S is in joules per Kelvin. Now, it's joules per Kelvin per mole, but remember, this is a delta S. All of these are ones, so it's a total delta S of joules per Kelvin for that reaction. Yep. 44? Positive 44? Negative 44? Negative. Yeah, I was going to say, we got some sign issues, but that's okay. Negative 44.0, and that's in kilojoules. And this is negative? Yeah, that's important. That's good. Because we want one that has the same sign. That's what I'm trying to get across. Perfect. So, is the reaction spontaneous, non-spontaneous, or reversible? Let's look at the signs. According to the delta H, spontaneous or non-spontaneous? Spontaneous. The universe likes this, right? In this one, this is spontaneous. How about this one? Does the universe like this one? No, not so much. This is non-spontaneous. And therefore, it is reversible. Reversible. Why is that? Because we have the same signs on delta H and delta S, and one's spontaneous and the other one is non-spontaneous. So this is a reversible reaction. It can happen in both directions. Does that make sense? Okay. If it's reversible, determine the equilibrium temperature. No need to rewrite the reaction again. You have it just above. I have it so I can just look at it on the slide for whoever's watching it. To determine the equilibrium temperature, we need to use our delta G information. If it is at equilibrium, what must be true about the delta G? Yep. It's equal to 0. It's right at that point where the enthalpy effect cancels out the entropy effect. Delta G equals delta H minus T delta S. 0 equals delta H minus T delta S. Bring that to the other side. T delta S equals delta H. T is equal to delta H over delta S. All right? And a very important thing that goes with this, must have the same energy units. All right? Those energy units must be the same. If they're not, you're going to be off by a factor of 1,000. What was the delta H? It was 44, wasn't it? 44.0? Negative 44.0, and that was kilojoules. Now, I need the delta S, but it also must be converted to kilojoules. What was it, 118.9? So I've got to move that over 3, and therefore it's got to be negative 0.1189 kilojoules per Kelvin. Must be converted. The kilojoules cancel out, and I have Kelvin on the bottom of a fraction in the bottom. What that does is it brings it to the top. That means my answer is in Kelvin. Notice the same sign cancels out. A common mistake for students is if I give you one that is spontaneous or is non-spontaneous. In other words, the signs are opposite. And I ask you to talk about the temperature. Many will do this calculation and will get a negative Kelvin temperature against the rules. Kelvin temperature stops at absolute 0. There is no such thing as negative Kelvin temperature. So you can only do this calculation with a reversible reaction. The signs must be the same. What do we get there for a temperature in Kelvin? Sorry? 370? 370 Kelvin. Now, I don't ask this all the time, but what is that in degrees Celsius? Does anybody remember how to go from Kelvin back to degrees Celsius? 273. Subtract 273. If someone could do that for just a moment, we'll take a look at that. Sorry? 97? 97? 97 degrees Celsius. Now, let's just think about this on a common sense point of view. This is a gas condensing down to a liquid. It's reversible, so we can think of it as a liquid becoming a gas as well. What temperature does gaseous water condense to liquid, or what temperature does liquid water become a gas? Yep, 100 degrees. That's the boiling point, right? That's the boiling point. So we obtained 97, which is pretty close to 100, simply by looking at its thermodynamic data. We didn't boil anything, we didn't measure anything, we didn't do anything, experimentally. We determined the theoretical boiling point for water is 97. That's pretty good, based on observations versus theoretical calculations. So that's the equilibrium temperature. At that temperature, we've got condensation and boiling happening at the same time, just as fast as one as the others. It's boiling and it's condensing. Determine the temperature range in which the reaction is spontaneous. So now I want to know, what temperatures do I need in order for that reaction to be spontaneous? And this has to do with the temperature effect. Again, probably no need to write the reaction again, it's just there for reference. But what I do need to know is the signs on our delta H's. You have them nearby, but when I think I remember them, this guy was negative and this guy was negative, right? Does that sound correct? And I want to know, what temperatures will it be spontaneous? When I'm asked to answer a question like that, I'm thinking about the temperature effect. Delta H negative T delta S. All right? So I'm thinking about the temperature effect. Now, I'm not going to do anything mathematically here. I'm just going to use some common sense and some logic. I want it to be spontaneous. I want to know what temperature range makes this reaction spontaneous. So I go back to my two thermodynamic factors, and I ask myself, which one of these supports a spontaneous reaction? Which out of our two supports a spontaneous reaction? TJ? The delta H. In this case, that negative is spontaneous. I'm now going to go back to my equation, and I'm going to ask myself, what type of a T is going to make the reaction spontaneous? What must happen to the T in order for the delta H effect to dominate through this situation? Yep. It needs to be small. It just needs to be lower than the equilibrium temperature. So that temperature that it needs to be lower than is 97 degrees Celsius. Because then at that point, this term is smaller than this term. Because at 97 degrees Celsius, the delta H is exactly the same size as the T delta S. They're balanced each other out. So if I want the delta H to dominate, then I need small t. Smaller than what? Smaller than the equilibrium temperature, because that's the balance point. Smaller than equilibrium temperature that we just determined. So in this case, temperatures that would make this spontaneous below 97 degrees Celsius or below what was it, 300 and something, 70? I don't remember what the number was. 370? All right? And that's how you deal with what temperature does it need to be spontaneous. All right, I have a second problem that looks just like this one. The only difference is I do want you to use delta G equals delta H minus T delta S, and I want you to calculate this delta G at 25 degrees Celsius. And then the rest of the questions are exactly the same. Is it spontaneous or non-spontaneous? If it's reversible, spontaneous, non-spontaneous, reversible. If it's reversible, determine the temperature, and then determine the temperature range that would make this thing spontaneous. At this point, I'm just going to pause the recording, and you can work away, and you can lean over to a neighbor. Okay, so again, I'm now recording again. I'm just going to write some of the information you guys just gave me. You guys told me that the delta H is positive 176.0, and we got to make sure we write our units down because it's going to remind us that we have to change one of them. That's kilojoules, and the delta S was also positive 284.8, and that's joules per Kelvin, so that's going to need to be switched. All right, and so I believe there was that first part of the calculation that we asked you to find a delta G at 25 degrees Celsius. It wasn't even part A, but at 25 degrees Celsius, then delta G is equal to delta H, oops, that's not an H, that's a T, delta H minus T delta S, delta H, 176.0, minus T, 25, that's Kelvin. 298, got to add 275. 298. And the delta S. Now be careful, I need to have a conversion of this 0.2848. And then that's going to get us kilojoules and then per Kelvin, but that's okay. We've switched it. Does somebody have a value for that delta G at 25 degrees Celsius? Sorry? You found the temperature at equilibrium? Is that what you did? That's fine. We're going to do that in a minute. But what I want done here is this first part that was different than the last one. This was different. I'm just asking, what is the delta G at 25 degrees Celsius? If we had this reactant, NH4Cl, and it was just sitting there solid on the desk at 25 degrees Celsius, what is the delta G value? What do we got? 91.2? Supporters on that? 91.2? 91.1? So one's a rounding situation? Not a big deal? Which one do you want? One or two? Well, you can't. We got to round it properly. You got a number right there in front of you? 91.1. Oh, and the lights are going out on us here. Yeah, 91.1 by the looks of it there. 91.1, and that's kilojoules. So at 25 degrees Celsius, all right, at 25 degrees Celsius, this positive part of the delta H is bigger than this negative chunk from the delta S. That makes this positive, which means at 25 degrees Celsius, is that reaction going or is it not going? It's not going. It's a positive delta G. Positive delta G's don't go on their own. So at 25 degrees Celsius, this is not spontaneous. Even though we're going to conclude in a moment, well, let's do that right now. A, is this reaction spontaneous, non-spontaneous, or reversible? What did you find? Spontaneous, non-spontaneous, or reversible? Yep. Reversible. How'd you know? They've got the same sign. They're fighting against each other. This is a reversible reaction. Reversible means it has the potential to go both ways. It can be spontaneous and it can be non-spontaneous, depending on the temperature. That's what reversible means. At 25 degrees Celsius, at this point, it's non-spontaneous. It's got a positive delta G. But it has the ability to be reversible because the signs are the same. One is supporting spontaneity, the other one is supporting non-spontaneity. So it's reversible because we have the same sign on delta H and delta S. I believe B asks, if it's reversible, what's the equilibrium temperature? Right? Is that what it's asking? Well, it's definitely not at 25 degrees Celsius, or the delta G would be 0. We need to set the delta G to be 0. When we do that and go through the motions, delta H over delta S. Delta H, 176.0. Delta S, 0.2848. They're both positive, which means I'm going to get a positive T. I have to have a positive T. And this is where we want that temperature. Courtney, what did you get there? Was it 618 Kelvin? We like that number? 618 Kelvin? 618 Kelvin. I don't need that in degrees Celsius because it's not a significant event like boiling or something like that. It's hot. It's got to be hot. All right. And the last question is, what's the temperature range in which we can make this spontaneous? In other words, the question is it above or below this temperature? Right? Is it above that temperature or below it? Well, remember, for determining spontaneity, I say go back to this. Which one of my thermodynamic effects is supporting spontaneity? The delta S, right there, that guy is spontaneous. So if I want it to be spontaneous, I want the term associated with it to be big. How am I going to get that number to be big? Sorry? It needs to be greater than 618. The T needs to be big. We need a big T in order to make the delta S big. Delta S is spontaneous. Therefore, need large T. And therefore, it's spontaneous at T greater than 618 Kelvin. So that's not decomposing on its own anytime soon. We need a pretty hot reaction vessel in order to make that decomposition take place. Okay? All right? I was going to do one more example, but I'm changing my mind and I'm going to use this slide for something else. So don't write down example 3. All right? And I'm actually going to then remove the last practice problem on that practice sheet. It has to do with boiling point or something. I'll talk about it in a moment. I do want to talk about one other thing. I've given you 2 examples of where the signs are both negative and where the signs are both positive on how to determine when it's spontaneous or not. I just want to add something here. Note, if delta H and, it's not example 3. I'm not doing example 3. It just came up. Ignore it. I've changed my mind on what I'm doing here. If delta H and delta S are spontaneous, right? That means if the delta H is negative and the delta S is positive. Where the signs are opposite, like I said. And I asked you the question, over what temperature range will this reaction be spontaneous? It's kind of a trick question, because what everyone wants to do is they want to use the equation and figure out a T. But there is no T that's going to work because the signs are opposite and you're going to get a negative value for the T. If delta H and delta S are both spontaneous, then the reaction is spontaneous over all temperatures. It means there's nothing that can be done to make it non-spontaneous. This reaction is spontaneous all the time, whether you're at absolute zero or whether you're at 618 Kelvin. So be aware of that. Sometimes I throw one in that has the opposite signs, and I'll say, could you please describe to me when it's spontaneous? And then some people will do the great big long calculation. They'll get a negative number. They'll do all the logic right, except if you get a negative number, that's against the rules. You can't have something colder than 0 Kelvin. All right? And I guess the second situation, if delta H and delta S are non-spontaneous, in other words, positive and negative, again, notice opposite signs, there will be no number that you can calculate, then the answer is the reaction is non-spontaneous over all temperatures. It's only where the signs are the same, and it's that you have that reversible situation where you've got that crossover point, that where it's hotter, it's either spontaneous, and colder, it's not spontaneous, or the other way around, depending on what you're looking at. All right? Okay, excellent. One more little thing to add on here. Ignore that question. I don't know if you noticed, but on your sheet, there's a delta G column. It's a delta G of formation. What chemists have done is, at 25 degrees Celsius, someone has calculated putting together the delta H and the S to calculate a delta G of formation. Now, how is this useful compared to what we've been doing? Let's say there's a chemical reaction that you want to study, and you know the reaction, and you don't care what the equilibrium temperature is, and you don't care what the delta H and what the delta S is, but the only thing you want to know is, in my laboratory, is that reaction spontaneous? That's all you want to know. You can add up the delta G's of formation, just like we did the delta H and the delta S, the same calculations, using the table, and you will get a value and a sign for the delta G, which means you can then look at it and say, oh, it's spontaneous, it's going to happen. Oh, it's non-spontaneous, it's not going to happen. So this kind of takes out the extra 2 steps of calculating the delta H's and the delta S's, because they're all built in to the table. This equation is just like the ones we've used with delta H and delta S. The sum coefficient, the delta G of formation of the products minus the sums of the coefficients and the delta G of formation of the reactants. So I'm not really teaching you anything new here, except you're looking at the next column. Okay? I simply have, is it 2? I was going to have 3. I simply have 3 examples for you to go through right now. Practice using the table 3 more times. All right? And then the next slide is telling you to complete the worksheet along with some review for thermodynamics. And that's the end. All right, actually what I'm going to do is, I'm going to just, I'd like to just advance to let you write this down, and then I would back this up and let you do those practice problems. Can we do that? Can we advance to write that down? You can maybe put that in the corner of somewhere or something. Then I'll stop the recorder as you guys are doing the practice problems there. And on that worksheet, which is that enthalpy worksheet from a couple days back, don't do the last question. Are we good to go? I'll bring it back then to that spot, and I will